Hello everyone, this is an implementation of a multi-function generator as a part of the Integrated Electronics project for winter 2021. Now this circuit can be divided into three parts. The first part of this circuit generates a sinusoidal wave, the second part generates a square pulse, and the third part generates an impulse train. LT-Spice has been chosen as the simulation tool, firstly because it generates reliable waveforms, and secondly because the models of most op-amps and transistors are readily available within this tool. So now let us consider the working of each of these three parts in detail. The first part is the sinusoid generator. As you can see, it has three LC oscillators in series, which is then fed through a feedback loop to an inverting amplifier. So each LC oscillator produces a phase shift which is equal to the inverse tangent of the ratio of the capacitive reactance and this resistance. So this works out to be roughly pi by 3 radians or 60 degrees. So three of these in series provides a 180-degree phase shift. And once again you pass it through a feedback loop to reach an inverting amplifier. So an inverting amplifier provides a phase shift of 180 degrees again. So the total phase shift is 0. And the LC or the capacitors in this LC oscillator store some energy and it expands it through the adjacent resistors. So finally you have a sinusoid which keeps on increasing in amplitude until it reaches a peak value. So now let us simulate this. So this is the simulated sinusoid. So if we zoom into this part to have a clearer view of how the sinusoid is being generated. So as you can see, it increases in amplitude until it reaches a peak value. And this sinusoid can be used for a variety of purposes like demodulating a double sideband signal and so on. So now let us move to the part where the square pulse is being generated. So this is done by making use of the technique of bad biasing of a transistor, wherein the operating point of the transistor is placed deliberately close to the cutoff or saturation point. So this means that the peaks of this sinusoid are chopped off, and what you end up with is a square pulse. So let us simulate this part. So as you can see, a square pulse is generated. It has a distinct positive and negative clock edge, which means that it can be used for a sequential circuit or a basic FPGA. Now this square pulse will be used to generate an impulse train. To generate the impulse train, we first need to consider the definition of the Dirac delta function. So it is essentially a triangle of unit area. So the first step would be to generate a triangle. So it's done by integrating the square pulse using an op-amp integrator. So this is then passed, since the output of this is really small in magnitude, it needs to be of some larger magnitude to be practically useful. So we pass it through a transistor based amplifier. So this is a common emitter amplifier, and it provides an impulse train output at its output. But the problem here is that it has peaks in both the positive and negative y-axis. So we then pass it through a diode to filter out the negative values, and finally we have a positive only impulse train in the end. So if we simulate this part, clicking on this generates the impulse train. So this is what the impulse train looks like. You can use it for a variety of purposes like sampling a signal at various time instances. You can also tune the frequency in one of these capacitors to change the overall frequency of the circuit. This implementation is different from the other implementations because of the lower number of op-amps used in this model. Other implementations use anywhere between 3 and 4 op-amps. So this has been done using 2 op-amps and 2 transistors, which means that it uses considerably less power.